Then we are going to have another shear line over here. Okay, and then point X is all going to be down here. Over here will be a point Y. And what's opening down here, this is our point Z. So now the 3D mold circle, the thing changed. So if I were to draw XY, right? This is our mold circle. Hold on, somehow it does not look right. Hold on. So I'm going to draw a straight line first. I join the both of them. And then our circle. So now this is different now. Okay, you can see it's different now. So now this belongs to our XY plane. And you can already see it's different because now our XY plane is the bigger circle, right? And then if I were to draw the other two circles, right, if I were to use a different color to sketch the other two circles, so over here, this belongs to our YZ plane. And then the last circle okay. So this now belongs to the XZ plane, right? So it happened that the XY plane is the tau max now, right? So now we discovered that over here this is our tau max, right? This is our tau max. And because it's the biggest circle, we also know that this tau max is this tau max over here, right? So to label this, right, this will be our stress max. Over here, this will be our stress mean. Okay. And then how to determine our stress max and stress mean? Okay, so we are going to formulate it. Okay, so we know that as before, we have our stress average line. Right? So this over here, this distance from here to here. So this stress average that we're going to use is for our XY plane. Okay. So now if we have to formulate our stress XY, okay, so we are going to calculate our stress average. Let me see, look at space. Yeah, I think we're okay. So we have stress average XY is equal to stress X plus by stress Y divided by 2, right? And then to find our radius, okay, to determine our radius, this will be equal to square root. Still the same. I think the formula still is valid. So is stress x plus by stress y divided by 2, right, squared, plus by shear xy squared. Okay. But the formula, because once you have stress max and stress mean, okay, one is in tensile. So stress mean for this case, the difference between this Mohs circle and the one before, right? Over here, the one before, this one for this case, stress mean is equal to 0, right? Which is over here. So this over here, this is our stress mean. And over here, this is our stress max, right? So if we look at this one, right, stress mean is not equal to 0 now, okay? So it's not difficult to calculate. So we know that stress max and mean is basically equal to the stress average plus minus, right? Maximum is plus, minimum is minus, then the whole thing square root of stress x plus by stress y divided by 2 squared plus by shear xy squared. Okay. So now if we were to plug back into equation number 3, right? If we were to plug back into equation number 3, so using equation number 3, right? We will have stress max is equal to stress x plus by stress y divided by 2 plus. You have the whole thing you square root, okay? Stress x plus by stress y divided by 2 squared plus by shear xy squared. And we also know that stress mean is equal to stress x plus by stress y divided by 2 minus now, and then we have this form. We have this form as in stress x plus by stress y divided by 2, the whole thing squared, plus by shear xy squared. Okay. So when we use equation 3, okay, I think my using equation 3 should be down here. Using equation 3, right, we know that the tau max is equal to half stress max minus by stress mean. Okay. So in this context now, if I put everything in, so what we have is we have stress max. Okay. I'm just going to copy and I'm going to just paste. Putting bracket. And then I'm going to minus again. We'll take this whole thing. I'm going to minus this term over here, right? And I'm close, right? So I can cancel this. I can cancel this. So this is in fact equal to tau max is equal to 1 over 2. And then absolute value twice of this term over here. Because minus and minus, when you take out the bracket, is plus, right? You have this term over here. And this is in fact equal to, once you remove cancel the 2 off, this value. So from here, you can see, right? So if you're, to quickly summarize, okay, if your Mohs circle looks like this, wait, let me, okay, so if your Mohs circle looks like this, right? If your mole circle look like this is the formula you use. Okay, if your mole circle look like this is the formula you should use. Okay. However, let me draw it bigger a bit. If your mole circle, if your 3D mole circle have this configuration, okay, if your mole circle have this configuration, and you can see the difference, okay? One, the circle is either both positive or both negative, which I align them. If your mole circle look like this, then your formulation for tau max changes. You have to use this equation now, or you have to calculate your tau max based on this expression over here. Then you have to apply this. Okay, so you can see the difference now, right? Both are Tresca, and also it dependent on how your mole circle looks like. Okay, the formulation is different. Okay, so if on a case where you have tau max is positive, tau mean is negative, this is what you have to use. But if your tau max, you only have tau max and your tau mean is equal to what? 0, it entirely changes. Okay, so you have to know, you have to first know how your 3D mole circle look like first. Okay, not 2D. You cannot do this in 2D. Impossible. Okay, I know textbook only draw 2D and have fun. No, you have to construct 3D mole circle. Okay, because in reality we're in a 3D world. Okay, and I'm not saying that 2D is not important. As you can see, 2D mole circle, you all learn how to draw mole circle using 2D, and 3D is just adding 2 more circles, right? So from here, okay, what I'm going to do is we are going to look into a real engineering problem. Okay, when I say real, this is as real as you can get. Okay, this is a typical real engineering problem that we see, or that I see as an engineer. Okay, so let's look at this example, and this example is pretty long. But it's a good example, I think. I hate it, not hate it, but the first time when I was doing it, it was pretty complex. Okay, but it's not that bad now. Okay, and I like to make sure it's not that bad to you also. Right. Okay, so you can find this example I posted on Avenue to Learn. Let's do 2 minutes to synthesize what this example is. Okay. Then we go for a short break. So the internal loading at a critical section along the steel shaft of a ship are calculated to be a torque of 2,300 pound-feet in bending moment. A torque of 2,300. So you can see down here, right? 2,300 over here. This is a torque. And you have a rotation down here to highlight that this is a torque. And you have a bending moment of 1,500 pound-feet. Okay, so you have this is our bending moment, 1,500. And then we are also given an axle load of 2,500. Okay, as you can see, this is a real 3D loading problem now. Okay, what is so fortunate for us in this case is we don't need to see what are the shear force, what are the point load to determine what is a torque, what is a bending moment, and what is the axle load is provided. Okay. So it also give to us the U point for tension. Okay, so we know that the U, right, in tension given to us is positive 100 times 10 to the power 3 pounds per square inch. So this is a material property given to us. Okay. And then the shear stress in yield is equal to 50 times 10 to the power 3 psi. So again, this is given to us. Okay. So what we have to do is determine the required diameter of the shaft using the what? Maximum shear stress criteria. So we know that using the maximum shear stress criteria, we know that tau max can be equal to stress max divided by 2, or tau max can also be equal to stress max minus by stress mean divided by 2. We now have to determine which one. Okay, by looking at this, by just visually looking, we don't know. Okay, we have to construct the element and we have to construct 3D Mohr circle. Okay, go for a 5 minutes break and we will come back again. Okay, go for a 5 minutes break.